Everything making sense so far? We're going to get deeper into propositional logic today. Thank you. All right, no questions yet. Um, let's eyeball homework 2 really quickly before we go on. So, a few more questions from the section on set theory. And let me just go ahead and bring up the text. So, just some questions on this business of summation and notations for summation. Let me freeze my chat window. All right, so questions 2, 4, and 10. Some details on question 2. Question 2 actually has 13 questions to it. So part A, you're asked to calculate this sum from k equals 1 to 3 of k to the n. Well, what is n? First, set n equal to 1, calculate this summation, give me the answer. Then set n equal to 2, calculate this summation, give me the answer. Same for 3, same for 4. So for 2a, you got 4 different answers, one for each of those cases. For b, it's just a single summation, sum from I equals 1 to 5 of 20. And then for C and D, you've got 4 problems to do for each of those, just like with part A. Calculate this sum for n equals 1, and then for n equals 2, and so on. So 13 answers total for question 2. Question 4 says verify. And verify is different from prove. Prove, we want to rigorously show something. We want to show that something is always true. We want to show that it necessarily has to be true. Question 4, we're doing something much less demanding. We're just verifying these equalities for the particular case where n equals 3. So it's not quite a proof in the sense of, filling up a blackboard with all of these rigorous arguments. It's really just suppose n is equal to 3. So this just says the sum from I equals 1 to 3 of this equals this sum plus this sum. And use what you know about addition and multiplication just from plain old, algebra, and try to show that if you start with this left side, you can rearrange things, replace things, change things to make it look exactly like this right side. And then same thing for B, show that the left side is equal to the right side. And then question 10, we're looking at the product rule. So this is like summation, but instead of adding these terms, we multiply these terms. For part B, we're doing a product of 100 expressions. 1 over 2, 2 over 3, 3 over 4, all the way up to 100 over 101. Don't do that explicitly. Don't type in 100 numbers and multiply them on a calculator. Don't write it all out, but write out the first few terms some way to express your answer as just a fraction of 2 integers. So not using factorials, not calculating decimal values and multiplying them, but just think about this product and see if you can write the answer as some number over some other number. And if you mess with it a little bit, you'll probably get there pretty easily. And then the other questions come from section 3. And these are some of the things we've already talked about and that we're going to talk about today. So 3.1 question 2, for each of the following propositions, identify simple propositions, express the compound in symbolic form, determine whether it's true or false. So let's just do A together. This is a proposition. The world is flat or 0 is an even integer. That collectively is a declarative statement. It has a truth value. But inside there, we can find smaller propositions. For example, the world is flat is a proposition. 0 is an even integer. That's a proposition. And so if I called this proposition A and I called this proposition B, then this whole thing I could write as A or B. So that's the goal of question 2, is to take these more complex propositions, define some simpler propositions. So for example, let A be the proposition, quote, the world is flat. Let B be the proposition, quote, 0 is an even integer. And then I could write this as A and a V, right, for or, A or B. And then I could decide whether it was true or false. Well, 0 is an even integer, so proposition B is true, so the whole proposition is true. So you want to do that for all 6 cases. And the point of this is we're going to be working with word problems where we're told, if the sun comes out on a Tuesday and it's raining, or I had hot dogs for dinner last night, but there was no mustard, then the winning lottery number will end with a 5, right? And we want to take that and we want to break it down into simple pieces, simple propositions that we can connect with logical operators and or not, and so on, so that we can start to analyze these word problems. So that's what we're getting with some practice with here in question 2. And then 3.2, we're looking at truth tables. So question 2, just construct these truth tables. And this is pretty straight engineering CSE 250, but it's good practice. And then 3.3, we got 3 problems. Exercises 2, 4, and 6. So let me do these backwards. Question 6, find a proposition equivalent to this that uses only conjunction and negation. So remember, 2 propositions are equivalent if they always have the same truth value. So find a different proposition that always has the same truth value as this, but uses only conjunction and negation. Question 4, X is a proposition generated by P, Q, and R, and it's equivalent to this. In other words, it always has the same truth value as this. Write out a truth table for it. So your truth table should have P, Q, and R for the inputs, and then X's value for the output. So 8 rows, 1 output column. All right, let's talk about question 2, because this one has some subtleties to it. So part A, construct a truth table for this proposition, X, which is P and not Q, or R and P. So just write out the truth table. That's just like the previous section. All right. Part B says, give an example other than X of a proposition generated by P, Q, and R that is equivalent to X. So let me write this down on paper and switch to my camera. So P and not Q, or R, P. All right. So that's our original proposition X. So write a truth table for part A. Part B, we want to find a proposition. I don't know, I can call it Y, such that Y is logically equivalent to X. All right, but don't just say X. We know X is equivalent to X. Technically, that would be an answer, but I want a proposition different from X, but logically equivalent. So do something to X to change it into a different proposition that has the same truth value in all cases. All right, part C says, give an example of a proposition that implies X. All right, so what does that mean? Find a proposition C such that C implies X. And implication is not the same as logical equivalence. It doesn't mean that C and X always have the same truth value. I want a proposition C such that if C is true, then X is true. So this takes some head scratching. Find a proposition C such that if C is true, then X is true. And then D goes in the other direction. Find a proposition D, and it says such that X implies that proposition. So find a proposition X such that, or D such that if X is true, then D is true. All right, so 4 different things. Construct a truth table, find a proposition equivalent to X, find a proposition that implies X, and find a proposition implied by X. These are really good exercises to kind of drill down into the idea of implication, equivalence, being implied by, and so on. All right, questions about that one? That's like the most confusing one of the batch. All right. So I'll get your homework graded hopefully sometime in the next few days. Um, I'll be grading it online. I'll post comments in the comment section of the submission area. We do not have class on Monday. Monday's a holiday, so we won't get together again until a week from today, which is when the homework is due. So strongly recommend coming to office hours if you run into questions, or shoot an email if you can't get to office hours. I'm planning to still do office hours Monday morning, so that will be an option. And then Wednesday morning as usual, but that's kind of tight for getting the homework turned in. All right, good to keep going. So we were talking about quantifiers last time. We talked about the universal quantifier, which says for all, and the existential quantifier, which says there exists. And I ended up with this exploration that if we take something like for all natural numbers x, p of x, that's just a big long conjunction of p of 0, p of 1, p of 2, and so on. And if we say there exists a natural number x such that p of x, that's a big long infinite disjunction, which says one or more of these are true. So let's look at these a little further. Um, this says for all x, p of x. I can be a little more explicit. For all x, p of x is true. When we just say p of x, we mean it's true. If I put a negation symbol in front of this, then it's saying it's not true that for all x, p of x is true. Well, if it's not true that for all x, p of x, What does that mean? It's not true that for all x, p of x is true. Can I phrase that in terms of an existential quantifier? So think about this. This says P is always true. This says P is not always true. How can I phrase that in terms of an existential quantifier? Suppose I wanted to prove that it's not true that for all x, P of x. What do I have to show to prove that this is true?
Find one value for which it's false.
Find one value for which it's false. If I claim for all fruits, the color of the fruit is red, and I want to show that that's false, all I have to do is find one fruit that's not red.
Couldn't not always true also be never true, though?
It could be, but as long as we find at least one case where it's not true, we can say it's not always true. If it's never true, then definitely it's not always true. So to prove that this is true, all we have to do is find that there exists one x such that not P of x. And if there exists at least one x where P is false, then we know that we can't say for all x, P of x is true. So we can bring this negation inside, but we have to switch the all to an exists. And by the same measure, there exists an x such that P of x. If there does not exist an x such that P of x, if there is no fruit such that the color of that fruit is rainbow, then it means for all fruits, the color is not rainbow. So we can switch the negation inside, but we have to swap the existential for the universal. So these are things to think about to get more familiar with these quantifiers and how they act and how they interact. Suppose I say for all x, P of x and Q of x. Can I rewrite that in a different form? For all x, P is true and Q is true. What else do I know based on that? So try some specifics. let's say P of X is the proposition that, so let's work over the universe of fruit. I don't know why I need fruit. For all fruit, the color of the fruit is red and the flavor of the fruit is sweet. Suppose that's true. Then this is also true, right? For all X, P of X must be true. And for all X, Q of X must be true. If I know for all X, this conjunction is true, well, if the conjunction is true, that has to be true and that has to be true. So for all X, P is true, and also for all X, Q is true. So this implies that. And in the other direction, if I know for all X, P is true, and I know for all X, Q is true, then I know that for all X, P and Q together are true. The conjunction is true. So these are logically equivalent. But suppose I say for all X, P of X or Q of X, and I try to do the same thing. Are these logically equivalent?
No.
Got a counterexample? You're correct.
All integers are either positive or negative.
Mm-hmm. So P could say all integers are positive, or P could say X is positive, Q could say X is not positive, negative. For all integers, X is either positive or negative. But this says for all integers, X is positive, or for all integers, X is negative. And neither of those are true. So these are not equivalent. And we can find a similar pair for the existential quantifier. If we use the existential quantifier, this will hold, this will not. So for some of these, intuition works. For some of these, intuition breaks down. All right, let's do one more. Let's talk about nested quantifiers. And let's just work over the integers. I'm not going to keep writing contained in Z, but let's just do everything on this page over the integers. For all X, there exists a Y such that X equals Y. True or false? For all X, there exists a Y. So if we want to disprove it, all we need is a counterexample. If we want to prove it, we've got to do some kind of reasoning to explain why this is always true. When I see for all X, that makes me want to start plugging in values of X and seeing if the rest of this is true. If I happen to pick an X where this is not true, then I can say, yeah, for all x, no, that's not true. So what if I set x equal to 0? What does this statement say? There must exist a y equal to 0, right? So it says there exists a y such that 0 equals y. And that's true, right? Because 0 is equal to y. If I set x equal to 1, this says there exists a y such that 1 equals y. Well, there is. That would be the number 1. So it seems like no matter what value of x I pick, I can always find a y equal to x. I just have to pick y equal to x. So yes, you're correct. This is absolutely true. All right, what about there exists an x such that for all y, x is equal to y? So here again, we can try some cases. Suppose I try x equal to 0. Now I only need to find one x where this is true. Suppose I try x equal to 0. What does this expression say?
All y must be 0.
Yeah, for all y, 0 is equal to y. And that's not true, right? 2 is not equal to 0. I could try x equal to 1, and this says for all y, 1 is equal to y. Well, that's not true because 2 is not equal to y, so that's false. And again, it seems like no matter what value I pick for x, this expression that I get is not always going to be true. In fact, it's usually not going to be true. So in fact, there is no x which makes this true. So this turns out to be false. And it's just by switching the order of the quantifiers. I could say there exists an x such that there exists a y such that x equals y. And that's definitely true. I could pick x equal to 0 and y equal to 0. 0 equals 0. Definitely true. For all x, for all y, x equals y. That's blatantly false. Because if I pick 0 and 1, 0 is not equal to 1. So there's no magic here. There's no punchline here. There's no rule I'm trying to get you to memorize or write down on your notes. We're just looking at what these quantifiers say from different viewpoints, right? It's the same definition of for all and there exists. But with those two definitions, we can look at different propositions and analyze them for their truth value. But there's really no punchline here, right? These are just exercises. But we can find some useful things in here. For example, for all x, for all y, x bigger than 0 and y bigger than 0 implies xy is bigger than 0. Well, that's true. And it's actually a really useful fact. It's our understanding that if we multiply two positive numbers together, we get a positive number. But here it is written in propositional logic form. So for all x and for all y, if x is bigger than 0 and y is bigger than 0, then x times y is bigger than 0. So more than just exercises, we can actually state a lot of useful properties using this relatively compact notation. All right, questions. There's a lot of silence, which is either coming from um, it's Wednesday and we're at the end of the week, or you're not sure how to use these quantifiers, or you're not comfortable enough with the definitions of the quantifiers um, to be able to even ask questions about what are you talking about. Um, there's some homework questions on this, which may help. Um, but let's switch gears. We'll let this sit for a little while. And let's get into kind of the heart of the subject. Fair enough. Yeah. Takes a moment to process the statements. Absolutely. And logic is one of these things that, we do at kind of a subconscious or slightly below conscious level. Um, when you hear an argument, you can kind of get a feeling whether it's correct or not, but not necessarily be able to say why. And one of the points of studying this subject is to get some tools to be able to actually analyze this stuff and take the intuition out of it. Or, when we have an intuition for something, be able to make that rigorous so we can put down on paper why something is true or not true in a way that we don't have to just say, well, just think about it. So that's what we're leading up to is this notion of formal proofs. And a proof you can think of as, you've got some insight and you know that this is true, you know that this follows from that, and you want to be able to convince somebody else. And so a proof is a standardized way that we can write down a sequence of steps so that if somebody starts with that, they can follow each of your steps and eventually conclude, just as you did, okay, this thing has got to be true. So this is tied in with rules of inference. And let me bring back um, page 50 from our notes. So we're going to be talking about this table 3.4.4, basic logic laws. I'm calling them rules of inference. Um, that's where we're going to spend the next few classes. So why are we talking about propositional logic? We want to be able to analyze statements and know if they're true or not. And truth is a tricky thing. There's some things that we can definitively prove are true or not true, and there's some things that we have no way of doing that. Science, for example, doesn't actually prove most things. Newton studied gravity, and we have Newton's law of gravitation, but science hasn't proven that that is true. It's an observation. It comes from studying data. It comes from an understanding of how objects interact, how forces work, and so on. But we've never proven that, you know, two massive objects attract each other, that if you drop an apple, it's going to fall to the ground. So in studying propositional logic, there's some things we cannot prove, but there's some things we actually can. So let me give you a few statements. So if it is sunny, then I'll go for a run. Now, you have no way of knowing if that's true or not, right? Maybe every time it's sunny, you look and you see me running by the window, but you still don't know if this is always true. But more likely, you're not watching my every move, and so you have no way of knowing if this is actually true. Could be true, could be false. Okay, here's another statement. It is sunny. Well, if you look outside, you can tell if that's true or not. But, where I am, it might be different. We live in a part of the country where it can be raining in one spot and like 10 feet away, it's dry. Um, so we don't know if this first statement is true. We don't know if the second statement is true. And we can sort of never know those things. But there is something we can know. What we know is the following. If this first statement is true, and if this second statement is true, then this is also true. Okay, there's a subtle difference here, so let me repeat this. We don't know if this is true. We don't know if this is true. We don't even know if this is true. But what we can say absolutely is the following. If this is a true statement, and if this is a true statement, then this is a true statement. So that's the nature of what we want to work with. This idea that given these two propositions, if we're told that those are true, we can conclude that this proposition is true. Does everybody see the difference between those? The difference between proving that this and this implies that versus trying to actually prove this or prove this or prove that by itself. It's a subtle but important distinction. So let's switch to the language of propositional logic. So let P be the proposition. If it is sunny, sorry, let me do this. Let P be the proposition. It is sunny. And let Q be the proposition. I go for a run. So this first statement, this is just if P, then Q. If P is true, then Q is true. And the second statement is the hypothesis, P. And what I am claiming is that if this is a true proposition, and this is a true proposition, you're guaranteed this is a true proposition. Another way to write this would be if P, then Q, and P implies Q. If this is true and this is true, then that's a hypothesis. If that hypothesis is true, then this conclusion is true. And sometimes to avoid extra parentheses, and the book does this, you'll see this written differently. You'll see this double arrow. And the double arrow means if the thing on the left is true, then the thing on the right is true. But if I got rid of the parentheses and I just had a single arrow, this looks like P implies Q and P implies Q, and that's ambiguous. So when we're doing proofs, we'll usually use this form because it's cleaner and easier to break down. But we can think of it as logically meaning this. When you look at it in the textbook, especially for the exercises, you'll see it in this form. They all mean the same thing. Okay, so there's a name for this. We can call it direct reasoning. It's also called detachment. It's also got a fancier name, which is modus ponens, which sounds like a dishwashing liquid or something. So in the textbook, they use the term detachment or modus ponens. If P, then Q, and P altogether implies Q. So that's a law of logic. And it's a law we're allowed to use in our proofs to try to prove other things. Okay, so let me give you some other laws of logic, and then let's look at why we care about this. Suppose I know if A, then B, and I know if B, then C, and I know if C, then D, and I know if D, then E, and I also know A. What can I conclude if I know that all five of these things are true? What else do I know is true? Using just this idea of direct reasoning or modus ponens.
B, C, D, and E are all true.
Absolutely. B, C, D, and E are all true. Direct reasoning tells me if A implies B and A is true, then B is true. And if B implies C and B is true, then C is true. And I can leapfrog like that, and I can absolutely conclude, hey, E is true, as well as B and C and D. So to do a direct proof of this is relatively few steps. To prove this with a truth table, I've got A, B, C, D, E, 5 variables. I'm going to have 32 rows in my truth table. And that's a lot of work. So we could do this exhaustively with a truth table, and a computer could do it easily. But for a human, it's easier sometimes to work with these laws of logic and get to the conclusion that way. All right, so let's talk about some of these laws of logic. So detachment, that's direct reasoning. Um, Indirect reasoning or modus tollens looks like this. P implies Q, not Q, therefore not P. So this is indirect reasoning. All right, so let's do an example. Let P be the proposition I win the lottery. And let Q be the proposition I buy a new hat. So P implies Q says, if I win the lottery, then I buy a new hat. And doesn't matter whether that's a true statement or not. For the sake of doing this proof, we're assuming that this is a true statement. So fix that in our minds. If I win the lottery, then I buy a new hat. And suppose this is also a true statement, not Q, which says I did not buy a new hat. Well, we can absolutely conclude I did not win the lottery. Why? Because this first statement says, if I win the lottery, I buy a new hat. And this says, oh, and by the way, I did not buy a new hat. You're forced to conclude, hey, I did not win the lottery. Right? Specifically because these two things would say, hey, I would buy a new hat, but I didn't. So P cannot be true. So that's how indirect reasoning works. All right, disjunctive addition. This is a way we can make a more complex statement out of a simpler one, which is useful sometimes. So again, P says I win the lottery. P or Q says I win the lottery or I buy a new hat. Well, if I win the lottery, then it's absolutely true that I win the lottery or I buy a new hat. Right? This right-hand side simply says, hey, at least one of P or Q is true. And the left side says P is true. Well, if P is true, then P or Q has got to be true. Because the fact that P is true makes this true, which makes this whole thing true. Conjunctive simplification. If I win the lottery and I buy a new hat, then I win the lottery. Right? If it's Wednesday and it's sunny, you can conclude that it's Wednesday. If it's Wednesday and it's sunny, you can conclude that it's sunny. So that's just saying if both of these things are true, then each one of these things is true individually. That's kind of the definition of what an and means. Disjunctive simplification works kind of in the other direction. If it's Wednesday or it's sunny, and it's not Wednesday, it's got to be sunny. If it's Wednesday or it's sunny and it's not sunny, it's got to be Wednesday. So if you know that one of these things is true and the first one's not, the second one's got to be true. If you know one of these things is true and the second one is not, then the first one has to be true. So it's a simplification based on ors or disjunction. Chain rule is what we were playing with over here. If A implies B and B implies C, we can take these together and say, hey, if A is true, then C is true. Why? Because if A is true, B will be true. And if B will be true, C will be true. So if A, then C. Right? If I win the lottery, I'll buy a new hat. If I buy a new hat, I'll look fancy. Therefore, if I win the lottery, I'll look fancy. Right? These things just chain together. Conditional equivalence, I think, is harder to find kind of an intuition behind, but we made a truth table for this implication statement, and we found out that it was equivalent to either P is false or Q is true. But remember, if we have P implies Q, that's almost always true. The only time this fails is when the hypothesis is true and the conclusion is false. So if you were to do a CSE 250 K-map on this, you would be able to reduce this to a simplified sum of products, which would be either not P or Q, right? Either P has to be false, that takes care of those two, or Q has to be true, which takes care of those two. So P implies Q is equivalent to not P or Q. Biconditional equivalence, this was our definition of that double-headed arrow. P if and only if Q means if P then Q, and if Q then P. And then contrapositive is this observation. Remember when we talked about P implies Q? We said there was the inverse, Q implies P, and that's different. Sorry, the converse, there's the inverse, not P implies not Q, and that's different. But there's also the contrapositive, and that's logically equivalent, not Q implies not P. So that's where that one comes from. All right, let's do a 5-minute break, and then let's try to use these two to do a proof of something. So let's come back at 12:58. Alrighty. So let's look at um a word type of problem and use some of these ideas. So here's a series of statements. If you send me an email, then I'll finish my homework. If you don't send me an email, then I'll go to sleep early. If I go to sleep early, then I'll wake up happy. Therefore, if I don't finish my homework, I'll wake up happy. All right, so there's four propositions, and the claim is that these first three imply that. So we're going to assume these first three things are true. If you send me an email, I'll finish my homework. If you don't send me an email, I'll go to sleep early. If I go to sleep early, I'll wake up happy. Therefore, if I don't finish my homework, I'll wake up happy. We claim that that follows from the first three. All right. And the question is, does this make logical sense? Let me move this out of the way for now. So we can't do anything with this in its current form. It's a word soup. So we want to change this into the language of propositional logic. What if you sleep early and finish homework without an email being sent? I don't know. That's possible. What this conclusion is saying, though, is that if I don't finish my homework, I'll wake up happy. It doesn't mean that I have to not finish my homework in order to wake up happy. It's an implication. If this, then that, right? It's very possible that I could finish my homework and still wake up happy. This is not saying that's not possible. Cool. All right, so let's try to put this into something we can work with, which means finding some propositional variables. So, I mean, I could make this whole thing the proposition P, Q, R, and S and try to prove P, Q, R implies S, but that's not going to get me very far. So I want to take these more complex, what we call compound propositions, and break them into smaller pieces. So I need some smaller propositions with which I can write these statements. So looking at this first sentence, what's a proposition that is a part of this larger compound proposition? So someone wrote email, if email, then homework. So that's what this first compound proposition says. What's a simpler proposition contained inside that?
You mean if P then Q, no?
Sorry, say again.
Uh, if P then Q,
If P then Q, what would P be?
uh, send an email.
Ah, okay, cool. So let's do this. Let P be the proposition. You send me an email. And then what's the proposition Q gonna be?
Um, I'll finish my homework.
I'll finish my homework. Perfect. All right, what about in the second sentence? There any new
Uh,
propositions?
if not P,
Okay, so that's not P.
then I'll go to sleep earlier.
Okay,
Mm,
so let S be the proposition.
yeah.
I'll go to sleep early. There's S again. If I go to sleep early, I'll wake up happy. So let H be the proposition. I'll wake up happy. So good. Those are good building blocks. So we can restate these now using these propositional variables. So if you send me an email, then I'll finish my homework. That's P implies Q. If you don't send me an email, that's not P. Then I'll go to sleep early. That's S. If I go to sleep early, that's S. Then I'll wake up happy. That's H. And the conclusion is if I don't finish my homework, so not Q, then I wake up happy. So this is equivalent to this using these values of propositional variables. And if we can show that this is always true, that this and this and this imply that, then we know in the particular case where these are the values of these variables, this will still be true, which means this paragraph up here will be true. So we might call this whole thing a theorem. It's a statement that we claim is always logically true. And what we want to do is prove that this theorem is always true. So let's try that. Let's say prove if P then Q, if not P then S, if S then H, implies if not Q then H. Now let me bring these laws of logic back in. So how do we do a proof? There's a few pieces to this. The first piece is to kind of stare at it and try to convince yourself if it's true or not. If it's not, then you're being asked to waste your time, right? But hopefully, if you're asked to prove something, it's actually true and it's provable. So then you might stare at it and think, why is this true? Right? If porcupines are allergic to raisins, why is perpetual energy impossible? And maybe you can find some insight, but maybe you can't. And if not, you can start just trying things. So this is where I made a suggestion a while ago that sometimes it'll be useful to do the homework on scratch paper, figure out how to get to the solution, and then write that up for what you actually turn in. Because if I'm not going to turn in the sheet of paper, I can do all kinds of scribbling on it. I can do all kinds of things that are, not things I'm supposed to do, but that I think might be useful. So I'm going to take this as scratch paper. So to prove something like this, I'm going to write the word proof. And here's what we're going to do. We're going to write down a series of propositions. And every proposition I write has got to be true. If I write something that's not true or something that I don't know is true, my proof is invalid. So everything I write has got to be true. All right, what are we trying to do? We're trying to say that given this, this, and this, we can conclude that. So remember when we started, I said, we don't actually know if these things are true, but we know that if this is true and this is true, then that is true. That's all we're trying to prove. We're not trying to prove that P implies Q. We're not trying to prove that not P implies S. We're trying to prove that if this, this, and this are true, then that is true. All right, so someone said starting contrapositive on P implies Q. All right, so that sounds like a good step. So here's what we're going to do. We're going to number every proposition. We're going to write the proposition, then we're going to explain why it is true. So if we're going to do the contrapositive on P implies Q, the first thing I'm going to do, step one, I'm going to say P implies Q. And why is that true? Well, I just said we don't know if P actually implies Q, but for the sake of the proof, we're going to assume that's true. So my reason for that, I'm just going to say hypothesis. Remember, we're trying to show basically a big, long if-then statement. We're trying to show P implies Q and not P implies S and S implies H taken together implies not Q implies H. Right? This is a wordier description of what we're trying to show. So this is the hypothesis, right? But it's also just the conjunction of three individual hypotheses. So I can state any of these things as being true in my proof and just say the reason is it's a hypothesis. Okay, so I can start off with if P, then Q. And then Brandon suggested do the contrapositive. So the contrapositive says not Q implies not P. And that's right here. If P implies Q, that's equivalent to not Q implies not P. So I have to justify this. Why am I allowed to write this? Because of something called the contrapositive applied to step one, proposition one. So I've got not Q implies not P. What else can I do? Just looking at this list of laws of logic, is there some other step I can take after this?
Not P implies S, which implies H.
Okay, perfect. So let's say not P implies S, which is a hypothesis. And then I think you're chaining that together with S implies H. So let's state S implies H. That's a hypothesis. And now I can use this chain rule and say, since not P implies S and S implies H, not P implies H. And my reason, my justification, is the chain rule applied to propositions 3 and 4. All right, good. What can I do next? The nice thing with proofs is the more you do, the more stuff you have to work with. So I've got like 5 propositions now, which presumably there may be more ways to put those together.
Didn't you
Looking at
chain
the end.
rule 2, 3, and 4?
Chain rule 2, 3, and 4. Not Q implies not P implies S, S implies H. So we already chained 3 and 4. So yeah, we could put 2 and 5 together. Not Q implies not P implies not H. So yeah, we can chain all 3 together, but let's do it 2 at a time. We already did these 2. So let's now say not Q implies H, and that's the chain rule of 2 and 5. Not Q implies not P implies H. So not Q implies H. Awesome. This is what we're trying to show, right? We're trying to prove if these 3 things are true, then not Q implies H. Well, using these 3 things and assuming that they're true, we just demonstrated not Q implies H. That's the end of our proof, right? We've shown what we're trying to show. So we put something down here. We say QED. And that's Latin for which is what we were trying to demonstrate. So our proofs are always going to end with QED. And QED comes after you've written the thing that you're trying to show. So if the last statement of your proof is the thing that you're after, then you can say QED, which means, hey, and that's what I was trying to do. And that's the end of your proof. All right, and then Julian asked in chat, couldn't we do this with indirect reasoning instead of contrapositive? Absolutely. There are often multiple ways to go about these proofs. So indirect reasoning says if P implies Q and we know not Q, we can conclude not P. So if we know that P implies Q, and we know not Q is true, that would get us not P, which would get us S, which would get us H. And so not Q would get us H. The reason we can do either of those is because indirect reasoning is the same as the contrapositive. So direct reasoning, P implies Q, P, therefore Q. That's direct reasoning. Suppose P implies Q and we're told not Q. So we can conclude not P. That's indirect reasoning. But if P implies Q, we can get not Q implies not P. That's the contrapositive. And if we're told not Q, we can conclude not P. That's direct reasoning. Right? So we can get there indirectly, or we can get there directly by starting with the contrapositive. of our first proposition. So indirect reasoning, contrapositive, very, very closely related. All right, this is what we're going to be doing for a while, these kinds of proofs. And the key takeaways are we want to begin with the word proof. We want to begin with what we're trying to show, right? So if you're doing a homework question, write out what you're trying to prove in the beginning. And then write the word proof. And then we write a series of propositions, all of which are true. There's a number on the left of each, starting with 1. And there's a reason on the right of each explaining why it's true. And if it involves a law of logic, we list which propositions are being used in that law of logic. For example, we took the contrapositive of proposition 1 to get this. We took the chain rule with 3 and 4 to get this, and so on. And then the last statement of the proof should be the thing that you're trying to show. And then you can put the word QE, the symbol QED at the bottom to say, yeah, and that's what I was trying to do, so the proof is done. So it's a very kind of formal methodology for writing up a proof. And the idea is if you handed this proof to somebody else who understands propositional logic, they would have to come to the same conclusion you did, which is given this, this, and this, that is also true. And there's no wiggle room. There's no interpretation like, well, I think you might not have meant exactly H, and if H was a little different, this wouldn't be true. There's no room for wiggling around like that, right? This is the beauty of this kind of logic, is it's unambiguous. It's not open to interpretation. It's not based on intuition. Now you use your intuition to figure out how to write this proof. And that's the part where, you need some insight, you need some vision as to why this is true. But once you've had that insight and you develop a proof, nobody needs to do any hard thinking to understand this proof and agree with it. It's very mechanical. So we're taking the kind of, mushy stuff that goes on in our head and turning it into something that can be shared rigorously and understood unambiguously. All right, good so far. Awesome. So if we're talking about proofs, you got to also touch on fallacies. And fallacies are things that look like laws of logic but aren't. And there's lots of things that, we can write that are simply not true. But there's a pair of fallacies, a pair of things that look like laws of logic that we can easily stumble into, but turn out not to be laws of logic. And they look a lot like direct and indirect reasoning. So let's talk about these two fallacies. If P, then Q, Q, therefore P. And this is called the fallacy of affirming the conclusion. And the other one is if P, then Q, not P, therefore not Q. And that's the fallacy of denying the hypothesis. All right, so let's look at some examples. Let P be the proposition I win the lottery. let Q be the proposition. I go to work on Monday. So this first statement, if P then Q, says, if I win the lottery, then I go to work on Monday. And that's true, right? If I win the lottery tonight, I guess there's a lottery tonight. If I win the lottery tonight, I'm still going to go to work on Monday because I wouldn't just abandon my classes. So this is absolutely a true statement. If I win the lottery, then I go to work on Monday. Suppose I go to work on Monday. Can we conclude that I won the lottery? Probably not. I'll let you know Monday. Right? So if P is true, then Q is true. If Q is true, we don't know that P is true. If P is true, Q is definitely true. But Q could be true all the time, regardless of P. So that's the fallacy of affirming the conclusion. Denying the hypothesis, if I win the lottery, then I go to work on Monday. I don't win the lottery, therefore I don't go to work on Monday. That doesn't follow. Because again, I'm going to go to work Monday regardless of whether I win the lottery or not. If I win, I'll go to work. But if I don't win, I might still go to work. In fact, I will. So these are not laws of logic. They're kind of the opposite. They're fallacies. And sometimes they seem really obvious, but sometimes they can pop up in subtle ways. And knowing that these are fallacies and being able to identify them can help us avoid slipping into this. Let's see, the second one is denying the hypothesis because it's not really using the hypothesis all right at all. Yeah, so these names are confusing to me. The only way I've sort of made sense out of them is looking at this piece. In this case, we're saying the conclusion Q is true, so it's affirming the conclusion. In this case, we're saying the hypothesis P is false, so it's denying the hypothesis. And it's a fallacy because by affirming the conclusion or denying the hypothesis, we try to draw some incorrect conclusion. So that's how my brain makes sense of which is which. And yeah, we're not using the hypothesis at all. That might be one way to think of it, is denying the hypothesis. Sometimes on tests, I'll ask you to identify laws of logic or fallacies. So it's good to be able to know which one of these is which. So you can put that on your sheet of notes for tests and such. All right. Other questions or comments on those? Yes. So Brandon notes, weirdly enough, both are doing the same thing if you use the contrapositive. Absolutely. Right. So they're really the same fallacy, just like direct and indirect reasoning are the same rule of logic if you throw the contrapositive in there. Same thing happening here. Cool. Nice observation. All right. So let's talk about proofs. We've already done a few of these. Let's formalize this idea of a proof. So we're going to work with theorems. Theorems are just statements that can be shown to be true. And the way we show them to be true is by writing a proof. So there's two main strategies to doing proofs. The first strategy is what's called a direct proof. And a direct proof is like what we did here. We started with the things that we know, the hypotheses. We applied laws of logic, and we eventually got to the thing that we wanted to show. So this was a direct proof. But there's a second approach we can take, which is called an indirect proof. And this is going to turn out just to be another contrapositive application. But with an indirect proof, let's say we're trying to prove X. So we start with not X. We take that as a hypothesis. And then we go ahead and we make a proof, and we come up with something absurd. Two equals 3. Well, if we can start with not X, then we can prove something absurd, like 2 equals 3. From that, we can conclude X must be true. Because if X is false, if not X is true, we get, 2 equals 3. And we know 2 doesn't equal 3. So in indirect proof, we start with the opposite, the negation of what we want to prove, and we argue until we get to a contradiction. All right, so two different approaches to proof. Future homework assignment, you'll get a set of problems to prove, and you'll do them both directly and indirectly. So let's do some examples. We've got about 20 minutes left. Let's do some examples involving integers. And I'm going to give you a definition. This is for integers. So an integer n is called even if there exists an integer k such that n equals 2k. In other words, an even number is twice some other integer. So 10 is even because it's 2 times 5. 12 is even because it's 2 times 6. 0 is even because it's 2 times 0. 3 is not an even number because I can't write 3 as 2 times some integer. It's actually 2 times 1.5, and 1.5 is not an integer. So we're going to say n is odd if there exists an integer k such that n equals 2k plus 1. In other words, it's 1 more than an even number. All right, so for the next 20 minutes or so, we're going to just work with these two definitions and try to prove some things. So let's start with this. Prove if n is even, then n plus 2 is even. Now, we kind of know this from experience, right? 10 is an even number, 12 is going to be even. If I add 2 to an even number, I'm going to get an even number. But let's try to actually prove this. And we're going to use a direct proof. So this is my hypothesis. This is the conclusion I want to prove. All right. the only thing I know is my hypothesis. Right? That's the only thing I have to work with. So step one, I'm going to say n is even. And my reason, that's a hypothesis. Well, I don't have a lot to work with. I don't know anything about n except that it's even. I don't know a whole lot of facts about even numbers. I'm not allowed to say if I take an even and add 2, I get an even. Even though I know that, it's not something we've been given. But I do know one other thing I can write, right? I know this definition of an even number. I know that since n is even, there exists an integer k such that n equals 2k. So that's going to be my next proposition. There exists an integer k such that n equals 2k. And my reason, that's the definition of even combined with proposition 1, which says n is even. All right, a lot of our proofs are going to start just like this. We're going to state the hypothesis, and then we're going to state some definitions to change this into something that we have more threads to pull on, more things to work with. So I started with the hypothesis n is even. I used the definition to write out this proposition. Now I've got 2 propositions to work with. Most of these proofs, you do some standard things in the beginning, and then you get stuck. And it's like, well, how am I going to get to n plus 2 is even? And so there's going to be something that happens here that we have to figure out. And once we figure that out, then there's going to be some steps that follow pretty easily that lead us to our final conclusion. But there's almost always this spot in the middle that we have to kind of like scratch our heads and wait for some inspiration to figure out what to do. So this is where it can be useful to kind of think out loud. So you can do this on your proofs. You can mark a section ignore and draw a line, label it ignore, and anything you do over here is fair game. I'm not going to take this as part of your proof. But you can think out loud on here. You can write things that you haven't actually proven, but that you want to prove. You can draw cartoons, you can do whatever you want, right? And it's not part of the proof because it's in this ignore section. So what would I do in my ignore section? I would look at what I'm trying to show. So I want to show, what do I want to show? N plus 2 is even. Well, what does that mean? It exists an integer such that n plus 2 is equal to twice that integer. So I want to show n plus 2 equals 2 times something where the something is an integer. Right? Totally not part of a valid legal proof, but it's in the ignore section, so it's totally fine. I want to show n plus 2 is equal to 2 times some integer. Well, take a look at what we've done. I've already shown n is equal to 2 times an integer. So I know n equals 2k. How can I show n plus 2 is equal to 2 times an integer?
N plus 2 is equal to 2 times k plus 1.
Nice. N plus 2 is equal to 2 times k plus 1. And if you didn't see that, I could just say, n plus 2 is equal to 2k plus 2. And then I could see, oh, I'm going to factor out a 2. So n plus 2 is equal to 2 times k plus 1. If I know that k plus 1 is an integer, I'm done. So there's another thing that you can use in these proofs. And this is what I'm just going to call closure of integers. And closure of integers is the following statement. If A and B are integers, then their sum is an integer, their difference is an integer, and their product is an integer. In other words, when you add two whole numbers, you get a whole number. If you multiply two whole numbers, you get a whole number. This is hard to prove, but we're going to take this as a fact. When we're working with integers, we can use this reason, closure of integers, to say, hey, if I take two integers, two whole numbers, I can add them, subtract them, multiply them, I get another whole number. Doesn't work with division, right? 2 divided by 7 is not an integer. But add, subtract, multiply, totally legal. So armed with that, since k is an integer, I know k plus 1 is an integer, and with algebra, I can show n plus 2 is 2 times this particular integer. And based on my definition of even, that's going to tell me n plus 2 is even. So there's the insight. That's the piece that will take some head scratching, listening to music, whatever. And we eventually see this path. Okay, now we have to turn this into a formal proof on this side of the squiggly line. So what am I going to do? I'm going to say n plus 2 equals 2k plus 2 equals 2 times k plus 1. And my reason for that is just algebra applied to proposition 2. And then I'm going to say k plus 1 is an integer. And my reason for that is closure of integers and proposition 2, which says k is an integer. And now I'm going to say n plus 2 is 2 times k plus 1. K plus 1 is an integer. N plus 2 is even. And that's the definition of even combined with proposition 3. N plus 2 is 2 times k plus 1. And proposition 4, k plus 1 is an integer. And that's what I was trying to show. There's where my QED goes. Does that look doable? So let's do one more and we'll call it good for now. And we're going to want to remember closure, and we're going to want to remember definitions of even and odd. So let's do this. Prove if n is even, then n squared is even. So 2 is even, 2 squared is 4, that's even. 6 is even, 6 squared is 36, that's even. If I take an odd number like 3 and I square it, I get 9, that's not even. 1 squared is 1, that's not even. 0 is an even number, it's 2 times 0, and if I square it, I get 0, which is even. So this should at least feel plausible. So let's prove it using the same idea. So statement 1, n is even. That's the hypothesis. Again, statement 2, let's just use the definition. There exists an integer k such that n equals 2k. That's the definition of even and proposition 1. And I'm going to do this again. I want to show n squared is 2 times some integer. And I know n equals 2k, where k is an integer. So how am I going to be able to show that n squared is also twice an integer? Nice. So let's just do substitution. Since I know n is 2k, n squared is 2k squared, which is 2k times 2k, which is 4k squared. And is 4k squared twice an integer? Right? If I hadn't actually multiplied this out, I would have seen this was 2 times 2k squared. So n squared is twice this thing. And this is 2 times an integer times an integer. And I've got this closure of integers, which says if I multiply integers, I get an integer. So k is an integer. Certainly 2 times k is an integer. And so 2 times that integer is even. Well, that's n squared. So there's the leap of intuition. So I'm just going to say n squared equals 2k squared equals 4 times k squared equals 2 times 2k squared. And that's algebra and proposition 2. And then I'm going to note 2k squared is an integer. And that's closure of ints. And the fact that k is an integer, which is also proposition 2. So proposition 3 says n squared is 2 times this thing. Proposition 4 says this thing is an integer. Put those together, n squared is even. That's the definition of even, along with proposition 3 and proposition 4. And that's what we were trying to show. So there's a few examples of direct proofs. And if you want to practice this more, there's all kinds of things you can show about even numbers, right? If n is an even number, I can prove that, n squared plus 10 is also an even number. And it would be a very similar proof. We can also do things with odd numbers. If n is odd, then it turns out n squared is also odd. And we can do that with a direct proof. And that's a good exercise to kind of get your own practice doing steps like this. All right, so we'll leave it at that for now. No class on Monday. Wednesday, a week from now, when we come back, we can review the idea of direct proofs, and then we're going to look at indirect proofs. And indirect proofs are another way that we can try to prove things. And it's going to be closely related to contrapositive of something else. So we'll do indirect proofs on Wednesday, and that will probably wrap up this pass through propositional logic. If there's time left next Wednesday, we'll start the next unit, which is number theory. And then after that, we'll come back and we'll go deeper into propositional logic. You should have everything you need to do the homework set, which is also due Wednesday. So take a look at that, send emails or come to office hours with questions. And if I don't have you in 222 tomorrow, have a good weekend, and I will see you next time. All right, thank you.